So, one of the more interesting series that we might want to know whether it converges or diverges is something involving sine or cosine. Something, for example, like this, where we have the sum from n equals 1 to infinity of cosine n over n squared. And we might think of using something like the alternating series test or the integral test, but we realize that we don't fit the conditions for either of those tests. And if we try something like the ratio test, we don't get anywhere. So we actually have to think a bit differently about this series. What we might ask is, do we converge absolutely or conditionally? So, we might ask whether or not we are absolutely convergent. Because absolutely convergent, remember, implies that your series is convergent. And so remember, to check absolute convergence, what we do is we're going to take the absolute value of whatever is inside our sum. So to check if we're absolutely convergent, what we want to do is take the sum as n goes from 1 to infinity of the absolute value of cosine n over n squared. And n squared is always going to be positive, so we actually move this absolute value up just into the denominator to make things look a little nicer. Absolute value of cosine n over n squared. And the one benefit of taking absolute value is that we know we're going to have a positive series. In which case we can use things like the conversion, we can use things like the comparison test, both limit and direct comparison. Theoretically, we can use the integral test. But any test where that works for a positive series will help us when we're checking for absolute convergence. Or it could be helpful if we're checking for absolute convergence. In this case, let's go ahead and try a direct comparison. So the one thing we know from our days of trig is that cosine of n lies between -1 and 1. The other way of saying this is that the range of cosine is between 1 and -1. And then we can write that might be a little more convenient, is to say that absolute value of cosine n is less than 1. And the benefit of this, and on the left-hand side, if we need, we can write 0 to remind ourselves. But the benefit of this inequality here is that we can do a direct comparison test. Because we have a cosine absolute value here, the only difference between this and this is that here we have n squared. So we know that n squared is always positive. So if we divide both sides of our inequality by n squared, we know that our inequality sign isn't going to change direction. It's going to get 1 over n squared. And so remember that with the direct comparison test, we know that if the sum of the stuff on the right-hand side converges, then the sum of the stuff on the left-hand side converges. So, the next question we need to ask ourselves is, does the sum as n goes from 1 to infinity of 1 over n squared converge? And one of the first things we learned about when talking about positive series is this notion of a p-series. And we know that 1 over n squared, the sum, does converge because our value of p is equal to 2, which is bigger than 1, right? So, because of p-series. And so what that tells us is that the stuff on the right-hand side the sum of the stuff on the right-hand side of our inequality will converge. Therefore, therefore, the sum as n goes from 1 to infinity of absolute value cosine n over n squared converges by direct comparison test with the sum of 1 over n squared. And therefore, the sum of cosine n over n squared, where n goes from 1 to infinity, converges, where am I at? Okay. Converges absolutely. And since we converge absolutely, we said that our series is thus convergent. So anytime you have a trig function like sine or cosine in your sum, one of the first things you might try is checking whether or not you're absolutely convergent. And then using a comparison like this that utilizes the range of sine and cosine.